Welcome. 2010 WA is an actual asteroid that came very, very close to Earth. Don't worry, if it was able to hit Earth, it would just dissolve on atmosphere. But we can imagine next time it comes close to Earth, we might want to send a robot to land on it, take a bunch of data. We might want that robot then to hop off and onto other asteroids, anything that comes near. So we'll imagine that the robot has landed on the surface of the asteroid and is chilling there for a little bit. The mass of our lander, or our hopper, is 20 kilograms. And the mass of our asteroid is 340 kilograms. Our asteroid has a radius of 3 meters and is a solid sphere. So when it jumps off of here, there's going to be something like an explosion where it has to expel some energy, so we do not have energy being conserved. Since we have this hop, we can't guarantee that the forces are constant, so we can say that the forces are not constant. But we could draw an interaction diagram where we have our hopper, we have our asteroid, and we have a force of the legs. This leg explosion force, and we can have then also our gravity. So our hopper is going to kind of hop off at an angle, both to get out, but then looking at it, we can say if we want, well, we don't really have to worry too much about the gravity, right? These are very small objects, but that we have angular momentum conserved. We don't have any outside forces, and then translational momentum conserved. If we wanted to know the path or velocity of our asteroid after, we'd use the translational momentum. Right now we're asking for period, which is an angular momentum thing. So if our angular momentum is conserved, we are saying the angular momentum of our system initially is equal to the angular momentum of our system finally. So let's find the angular momentum of our system initially. It's the angular momentum of our asteroid initially, plus the angular momentum of our hopper initially. So these two are both rotating with the same period, the same omega. So we can then say it's equal to I times omega. The I of our asteroid is going to be that of a sphere, 2/5 m, 340 kilograms, r squared, 3 meters squared, times our omega, which is 2 pi over 35 seconds. Our hopper is very, very small and dense compared to our asteroid, right? It's made of steel, our asteroid's made of roughly dust. So we can treat it as a point particle without too much things gone wrong, which is then just the I is mr squared, so our m is 20 kilograms, our r squared is 3 meters squared, and our omega is still this 2 pi over 35 seconds. So now we have just numbers. If you want to plug this into your calculator, great time. I've already plugged it into my calculator. The angular momentum of our system initial is 252 kilogram meters per second. Meters squared per second. And so then we know that our angular momentum of our system final must be equal then to 252 kilogram meters squared per second. And that must be the angular momentum of our asteroid final plus the angular momentum of our hopper final. So the angular momentum of our asteroid final is going to be the same I, 2/5, 340 kilograms, 3 meters squared, times the period, 2 pi over our new period, plus the angular momentum of our hopper, which we'll do on a new line. So our hopper now is just a particle moving. So it's starting out just away from it, so it's still got 20 kilograms. And we can use instead that L is equal to mv cross r. So we've got m, and then our v is 14 meters per second. Our crossed with our r, which is 3 meters. And then we would take the sine of the angle between the two, sine of 20 degrees. So we can do this cross product, right? It's the magnitude of these two, the magnitude of this one, times the sine of the angle between them of 20 degrees, right? If this flew off exactly out, then our period wouldn't change, but because it jumped off at an angle, our period does change. And so then, as we can do this, then we have 252 kilogram meters squared per second is equal to 1224 times 2 pi over our period plus 287.3 kilogram meters squared per second. So calculating all this, right, our omega final is going to be negative 0.0286 radians per second. Our period is going to be 220 seconds. But because we have this negative, right, it's in the opposite direction. So this jumping off has given such a torque in this idea that it's gone from rotating this way to now rotating this way. So this is a good example of an angular momentum problem. Since there's so much in angular momentum, we're not going to worry too much about elastic collisions. It's going to be either inelastic or explosions like this one, where essentially we're going to have just a one equation, one unknown.